Hello Surveyor 3s. In this third video of the DGNSS series, we will take a closer look at the various forms of GNSS errors and how they affect accuracy. There are many factors that make it difficult for a GNSS receiver to calculate an exact position. Let us discuss these factors one by one. The first error is the satellite clock error. GNSS satellites are equipped with atomic clocks to provide precise timing signals. However, variations in the satellite clock can introduce errors in the ranging measurements, affecting the accuracy of position calculations. Different global systems use different type of atomic clocks, and most satellites will have multiple types of clock on board. For example, rubidium and cesium are standard on GPS. Galileo has hydrogen mesa and rubidium. These clocks are incredibly accurate, but they are in perfect and experience drift. This means they lose or gain 1 nanosecond for every 3 hours of time. For example, 10 nanoseconds of clock error results in 3 meters of position error. Next is the orbit error. GNSS satellites travel in very precise, well-known orbits. However, the orbits do vary a small amount. A small variation in the orbit results in a significant error in the position calculated. Here, from the image, you can see that the satellites are not on the calculated orbit, which in turn affects the position determination. In order to keep the ephemeris precise, the satellite orbits are permanently monitored by the GPS ground segment. The data from the observations are used to calculate the orbit data in advance. The newly calculated orbit data is then transmitted to the satellites and updated hourly. To get even more accurate orbit data, the satellites are not only observed by the GPS ground segment, but also by a large number of worldwide distributed observation stations. This error source can be reduced by means of relative measurement or by post-processing. Another error is the ionospheric delay. The ionosphere is the layer of atmosphere between 50 and 1000 km above the Earth. This layer contains electrically charged particles called ions due to solar radiation. These ions alter the transmission time of the satellite signals and can cause a significant amount of satellite position error, typically plus or 5 meters. Here from the figure, we can see that the signal from the satellite propagates in a straight line and at the speed of light. Upon entry into the ionosphere, a part of the wave is reflected at the interface, while the other part of the wave is refracted at the interface. Thereby, it results in a propagation delay of the satellite signal. The reduced propagation speed of the satellite signal causes a delay of the signal. This is generally the largest error source in GNSS measurement, but it can be reduced by using relative or multi-frequency measurement. Next, we discuss the tropospheric delay. The troposphere is the layer of atmosphere closest to the surface of the Earth. It is approximately 8 and 14 km deep, depending on the location on the Earth's surface. Tropospheric errors are caused by temperature, density, pressure or humidity changes. Here, the GNSS signal is mainly affected by water vapor, which varies in a lot of time and space. The next error is the multipath error. Multipath error occurs when a signal from the same satellite reaches a GNSS antenna via 2 or more paths, such as reflected off the wall of a building. The reflected signal clearly has to travel further to reach the antenna, and so it arrives with a slight delay. In an environment with tall houses or trees, multipath errors are more common. Also, to reduce multipath errors, Place the GNSS antenna in a location that is away from the reflective surface. And finally, we discuss on the receiver noise error. Receiver noise refers to the position error caused by a GNSS receiver hardware and software. All GNSS receivers are subject to other radio waves that occur naturally or through other processes. These other radio waves, along with the other type of electrical interference, are what is known as background noise and impact the ability of the receiver to hear the GNSS signal. High-end GNSS receivers tend to have less receiver noise than lower-cost GNSS receivers. Calibration and signal processing techniques are employed to minimize these errors, but they can still impact accuracy. With this, we come to the end of the video. I hope you understood the different GNSS errors and how it affects accuracy. In the next video, we will discuss the base and the rover concept. Those who are watching the video for the first time, please like and subscribe. We will be adding more videos weekly. Click on the bell icon so that you won't miss any upcoming videos. And thank you for watching the video.